Okay guys, we've been talking about what's inside the computer here. And the computer is what's either giving power to the switch or the switch is giving power to the computer, okay? So I want to take the computer now out of the scene, okay, just for now. I want to bring back some more simplicity to try and reinforce what I've been saying, okay? So let's just move on. Okay, let's just go back to a really basic, really simple light bulb as our load, switch, battery, ground. Very simple. So here we have our battery, our fuse. We always have a protection in our circuit, so we put a fuse in there. That's our light bulb. There's our switch. What type of switch is that?
Pull down switch.
Yeah.
Toggle switch.
It's a pull down switch and it's a switch to what?
Switch to ground.
Switch to ground, okay? Very important. Could I have that switch on this side?
Yes.
I couldn't I?
Yes.
Doesn't matter, does it? It still does the same, okay? So, I want to ask you, what is my voltage, if I had a voltmeter here, what's my voltage to ground?
Zero.
Zero. Good work, students. Good work.
Wait, answer the bhaiya.
And exactly. Zero. Okay? Why is that?
Because the circuit is closed.
The circuit's closed to ground,
Yeah.
and all that voltage has been pulled down to zero. Okay? All right? Okay, what happens now? I've opened the circuit.
12 volts.
Get 12 volts, don't I? Okay, because we're reading the voltage going through the fuse, going through the filament of the bulb back to there. That's why it's 12 volts. There's no current flowing. So what we have?
12 volt.
We're not being pulled down, are we? The voltage is not being pulled down. That's important to know because when we do some of our diagnostic work with electrical things, we need to understand that. Just imagine, okay, my light didn't work. Okay, if my light didn't work, and I go to the switch, which is on the ground side, and I check for voltage, and I've got 12 volts, what's that telling me?
Bulb is destroyed.
Not necessarily. Not necessarily, okay? It's telling me I have a good circuit through the bulb filament, through everything to there, okay? So where do I concentrate my problem to?
Bulb.
No,
What the?
switch and ground.
Yeah.
So my problem is now in this area, no longer in that area. How much time have I just saved? How much time have I saved?
A lot.
A lot of time. That's why I'm teaching you all this. It helps us with our thinking and our diagnostics. Obviously, we have to understand the circuit. Obviously, we need to understand the wiring diagram. That's how we learn the circuit, okay? So we know where the power comes in and where the ground is, which side of the switch it is. Otherwise, if we don't know that, this doesn't help us, okay? All right. Again, go back to the computer again. And now we've got an opposite. Before we had this grounding, I should say. Now we've got power going into the computer. The opposite, haven't we? So now with the switch open, we've got 0 volts. Does that make sense?
Yes.
Before, when it was grounding and we had power going out of the computer, we'd have the battery at 5 volts, wouldn't we? Or whatever the voltage was. Okay? But what happens now when the switch is closed?
12 volt.
12 volts, okay? 0 or 12. See how the computer reads things from the inputs, okay? So we'll simplify it again, go back to our bulb. And again, here we go, the simple circuit. But this time, where is the switch?
Switch is on the
On the
positive
power side.
side.
It's a pull-up switch, it's on the power side. Okay, so if I measure the voltage from there to there, what's it going to be?
0.
0. We're doing well class. Again, okay? Again, if I was to, if I had a closed circuit and I measured voltage here on a closed circuit and I actually had 12 volts, what would that tell me?
The circuit is open somewhere.
Yes, yes. And what side though is it open on?
Positive side. Oh,
It has to be, if I've got my pointer somewhere here,
ground
and
side.
I got 12, it's got to be down that way, it's open. Does that make sense?
Yes.
Okay? Again, we save time by knowing this when we're looking at things. Again, we'll start with the voltmeter. Oh, hang on.
Shit, my brain's gonna explode.
Okay? I've got 12 volts with the switch closed on that side. I'd have 0 volts on that side. Know that. Because the switch now, we're looking forward to the switch, but on the power side. Does that make sense?
Yes.
So if I put the voltmeter there, it would be 0. There, it would be 12 volts. So keep that in mind.
Yes.
Jerry, are you understanding? Okay. Jerry. Here's my resistor. Here's my bulb.
Yeah.
Okay? I'm going to have power on this side. So here's my switch. I've got power on this side, right?
Yeah.
But say I didn't have a ground there. I would have 12 volts there. I'd have 12 volts there. Is that correct?
Yes.
If I had an open circuit here.
Open?
If this circuit is open and I got 12 volts going into it, it's not a closed circuit. No matter where I put my voltmeter on that circuit, I've got 12 volts, okay?
Yeah.
But now I've closed the circuit. It's going to ground. And I've put my voltmeter on this side where my power's coming in. I'm going to have 12 volts or whatever the power voltage is because it's going in. But what comes out where it's on the ground side will be 0 volts. Does that make sense? So if you look where I put my voltmeter now, what side am I on? The power or the ground side?
Power side.
The power side. So I'm always going to have power there regardless of whether the switch is on or off. But if I move my voltmeter to this side, on the other side of the resistor, while it's grounded, what's it going to be? Zero. Who's following? Who's following or who's not following? It's important you get that. This is very Brian, what are you doing?
Following?
I pick on Brian when he sits up here, so now he thinks I can't pick on him, but I prove I can. I'm only kidding. Okay. This is a very, very important, basic, foundational thing that you all must understand. Okay, if we want to be able to diagnose electrical things, we have to. Where's Abby?
Isaac?
And Isaac. Don't worry about Brian. You stand down here. Okay, Brian. Abby tells me he wants to understand all this. He wants to be a good technician, but he doesn't come to class. Anyhow, power going through the resistor to an open circuit is going to be wherever I put it. It's going to be the power source. As soon as I close the circuit, the side that's grounded is always going to go to 0. All the voltage is drawn to 0. The side that's open, the side that's on the power side is always going to be the power source voltage. Pretty simple, eh?
Yes.
Is that simple?
Yeah.
Okay. It doesn't get any simpler.
Makes sense.
Makes sense. What my job is to teach you to think auto electrical, okay? At the moment, this is my job. With mechanical things, it's really easy to understand because we see things. With electricity, we don't necessarily see electricity, but we can read electricity. And so we have to know what we expect when we do a test, when we read the electricity. We have to know. Guys, you guys are 10 minutes late. Okay. All right. Any questions?
Oh, good.
Is there anyone, and I mean this, I'm not trying to embarrass anyone, does anyone not quite understand what I'm saying? Everyone's on page? Okay, let's move on.
Maurice, is
Yes.
there any chance that we can try it actually?
I hope to, but Guys, I haven't told you this, but I'm only here until 12 today. Okay, I got
Yes.
a funeral to go to this afternoon. So I have to pump a lot of things in. So tomorrow, yes, we'll play with this tomorrow. Okay?
Here?
At the workshop.
At the workshop.
Okay, we'll do a bit more at the workshop. Okay, I'll do my best. All right. No talking, no talking. You've got to move a bit, you've got to move a bit quicker now, so be quiet. Okay, again, now the switch is open. Okay, see how we've got no power, 0, because the switch is open there, at the same point before we had voltage. Notice where I got the fuse. Have I made a mistake putting the fuse there? And should I be having the fuse before?
Yes.
Who thinks yes, who thinks no?
I think yes.
I think after the switch.
Alright, I'm going to tell you something. If I put the fuse here, will it be effective or not?
No.
Why?
Because the load is.
Why wouldn't it be effective?
There will be a constant voltage, ground voltage. So
What causes a fuse to blow?
load,
So much
Not
load.
low,
high voltage,
not high voltage.
low.
High voltage.
I want to hear what happens. What happens when the electrons flow?
The fuse file.
Yes, but what do we use that terminology? What happens when we light up this circuit and we complete the circuit? What happens?
Trip.
When we close the circuit, what do we get?
Current flow.
Current. Who said current?
Musa.
Loser. Current flow,
Lollipop loud.
high current flow or high
Lollies.
amps is what causes the fuse to blow.
Both very
Who
disturbing.
knows that whatever current's flowing here is also flowing here? Whatever current's flowing there is flowing here.
Yes.
Makes no difference. Makes no difference where I put the fuse. Okay? It will blow. No matter where I put it, it'll open circuit if we have excessive current flow. That,
So if you put it after the light,
if I put it up the light, it's not, that's the
so
same.
will the light burn first or the fuse?
No, when we get high current, okay, the fuse will run.
Even if it's after the light?
Well, debatable. Debatable, but the fuse is more likely to go because it's protecting the circuit. So we don't put too high in here, okay? If we have too high current flow to the bottom.
Order.
Quiet! But my point is, we put a fuse in cars, generally in the power side, nearly always in the power side.
Yeah,
Very
always.
rarely on the ground side. And that's fine. But I just want to get across to you, it doesn't matter where the fuse is, as long as we've got a fuse.
But the best way is to put it on the positive side.
Only because that's how we've been taught and that's what we do.
Yeah.
Because the main power comes from the positive side.
Most of, and I guess we think of the fuse as our power, because that's how it's always done.
Yeah.
But I just want you to think outside the box a little bit.
It can be
doesn't
put
matter.
anywhere.
It can be anywhere,
Yeah.
okay? All right, let's move on.
Anyway, after the switch.
गुस्सा नहीं करो.
Can't put it before the switch.
I thought I'd put these two together,
Otherwise a
right?
miracle will happen.
Okay, just to show you, I pull down is where the switch is grounding the circuit. So 0 volts, 12 volts. Then we move to the pull up where it's powering up, and the difference, the opposite. So we have the opposite. It's important we know whether it's pull up and pull down, so we know what to expect when we put our voltmeter on. Okay? Just, how do we know?
Well integrated.
We saw that, I thought that Paul Denner video was really good, and maybe it would have been good to show you afterwards after I explained things, but again, because you probably missed a lot of things that you'd pick up now. So it might be a good idea sometime to re-look at that video. You've got access through it. When you do your assessment, where it says information, it will open up to all my PowerPoints, it will open up to my videos, I'm pretty sure, okay? Have a look at it. Okay. Again, I want to change now, I want to add a real load in the system as well. who knows what a cam angle or even a crank angle for that matter, but in this case it's or it can be either. When we put a sensor in the as a switch now, we're not looking at a physical switch, now we're looking at an electronic switch, okay? Electronic switch, for example, in a Hall effect cam angle or crank angle sensor, it will actually give us a signal, okay? Where's my pen? Who's got my green pen? Throw it up. My whiteboard pen, yeah, that one. Oh, great catch. Put me on your cricket team, will you, eh?
What do you think?
I believe Australia did well in the cricket, eh?
Yeah.
Never hard
Better than the Indians.
Yeah.
Who do you back?
Huh?
Who do you back, Australia or India?
Fiji.
Australia won, so we support Australia.
Whoever wins is the boy. So I have a daughter-in-law who's Indian. Her family obviously support India. My son's Australian, so obviously he supports Australia. So there's a bit of conflict in that family. Okay. All right.
She'll
So
be fine soon.
a whole effect sensors like this.
I'm gonna miss the shell be fine.
Bye, motherfucker.
So here we have 0 volts. Here we might have 5 volts. It's just argument's sake. It's an on off. Yes.
Is it the same installed in the ABS system?
Yeah, yes. Yeah. If it's a Hall effect, Hall effect is a digital sensor. A lot of, well, not all, but some speed sensors, wheel speed sensors are analog. You know, analog reluctant type sensor, which is up and down, positive, negative sensor, which then is converted in the computer to a DC or a digital pattern. Okay, but this is 0. So this is your switch. The switch is going on and off, except it's an electronic switch. Okay. So what I want to show you is this Hall effect sensor. It has 5 volts on the signal wire going into the sensor. It also has maybe a 5 or a 12 volt power going in. It also has a ground. Okay. So that particular sensor is a pull down because power from the computer is going to the switch and the switch is pulling it down to 0 volts. Pull down. Okay, it's the same thing. Think of our light bulb. If the switch is on, it grounds. When we pull down, it grounds. The Hall effect sensor is grounding. Okay, it's grounding and it's doing the same thing. So that is a Hall effect sensor that's a pull down. But you know what? We could have a Hall effect sensor that's a pull up sensor. Could be one or the other. Okay, they're not all the same. Here we go. Pull down. This one here is a pull up. So in other words, the signal wire, is feeding the power into the computer, whereas before the computer was feeding the power into it on the signal wire. Okay, it still pulls down and up, but it's done. The sensor is actually turning the power off and turning the power back on by shorting the power to pull it down to 0 in the sensor. And every time there's power going into there, this is being pulled down by the computer and takes a reading. It'll either read 0 or 5 volts or 12 volts, whatever it's putting in there. So it can be a pull down, it could be a pull up. How do we know if we have a crank angle sensor, which sensor we're dealing with? How do we know? If the wiring diagram doesn't tell us, which they probably don't, how do we know? What if I told you, if we pull the plug from the sensor out, okay? We pull the plug out and we test to see if there's voltage there. If there's no voltage after we pull the plug out, we'll have one that's got power. There's always power going into those sensors, always. But the signal wire will either have power or not have power. So if we pull the plug out and we've got one only that's got power on there, guess what? It's going to be a what?
Pull up.
Or pull down. Pull up. Okay? And if it does have power, it's going to be pulled down. Does that make sense?
Yeah.
Okay? So we pull the plug out to check. Alright? So, this one's got 5 volts there. This one has 5 volts coming in. Okay?
I'm confused. Have
I confused you?
Yes.
Yes, sort of. Before you said,
Have I sent it right back to front? Let's go back to the last slide.
yeah.
Okay. So this one is pulling 5 volts into the switch, okay? So if we pull the plug out, okay, will we say 5 volts there? If we pull the plug out?
Yes.
If we unplug the sensor?
No.
Because we have 5 volts always.
Yes.
This one is feeding from the computer, 5 volts. Sorry, signal wire, 5 volts. See that? And that sensor pulls it down to ground. The sensor is our switch. This is our power, okay? There's our resistor there. We've got 5 volts going through here. Then that will pull that down to ground.
So will the power have 12 volts or 5 volts?
Well, in this case, it's a 5 volt reference signal wire. Okay?
So we'll get the.
Power will either be 5 or 12 volts. It doesn't matter. It's
So
immaterial.
when the lug is out, we'll get the power in the signal wire.
Yes, because there's no completed circuit and the voltage is coming from the computer waiting to be pulled down. Am I making sense?
Yes.
Are you making sense?
Yes.
Who's not following? What's complicated things is I've put a electronic switch in there. You got to think of that as a normal switch thing, okay? So if it wasn't an electronic switch, we would not need the power going into it. Do you understand? But because we need the power going into it, because it's an electronic switch, it just puts another dynamic in the circuit. But if we ignore that, at the moment, we realise that we have 5 volts going here, and the switch is putting it to ground to complete the circuit.
But why it is confusing? यहाँ पे signal में out.
We have a load here, we have a load there, it's going nowhere until it gets ground. Just like our light bulb, okay? That light bulb, when the switch is open, the voltage is going nowhere until we turn the switch on. And when we turn the switch on, it goes to ground. Okay, let's go back. So we go back, let's go back a bit more. Okay, let's go back to the pull down. Pull up and okay, here's our pull down switch. Okay, see that light bulb? That light bulb is my cam angle sensor. Okay? Oh, sorry. No, that switch is my cam angle sensor. That light bulb is the resistor that we had. Okay, that's the resistor. So we've got the voltage here. Until that switch is closed, we have voltage always. As soon as that switch is closed, we have 0 voltage. Okay? So if this is my sensor and I unplug it and I test that wire there, what have I got?
12 volts.
I've got the voltage, 12 volts. Okay? Because this is a pull down, I've always got power going to the switch. Until it's closed, that power is open circuit, so it's not complete circuit until the switch closes. Alright? Go forward again. Again, it's open circuit, so we've got 12 volts there. Okay? As soon as that switch closes, we've got 0 volt. On our Hall effect sensor, when the switch is closed, we have 0 volts. When the switch is open, we got 5 volts, 0 volts when it closes. So the only difference is, this is a mechanical switch. The Hall effect sensor is an electronic switch, okay? And it's working off, when the engine's rotating, okay? We have a magnetic field, every time that magnetic field gets disrupted, it creates an induced voltage for a split second. That induced voltage is enough to turn the transistor on and off, on and off. So that's how a transistor works. It goes on, off. Every time the two magnetic coil and the magnetic coil is fed in by that other 12 volts in that ground. You know that how we saw a permanent 12 volts or 5 volts going to the Hall effect sensor? That's because it's creating a magnetic field inside that sensor. And that magnetic field gets interrupted by the passing of a conductor that's been rotated around. And every time it comes up to the reluctor wheel, that's the conductor, it gets disrupted and creates its own little voltage for a few seconds. Well, not even seconds, a millisecond time frame where the sensor gets turned off and grounds and then gets opened up again to be 5 volts again. Is that making sense?
Yes.
Is that making a little bit of sense? Good. So, this is why I put these basic circuits in, to try and help us understand. Oops. Oh, what have I done? Okay, look. So again, here's our pull-up circuit, right? A pull-up circuit, the power goes to the switch, and the switch feeds the power through to the load. So that's the difference, okay, on a pull-up to a pull-down. Okay, the switch controls power. On a pull-up, the switch controls ground on a pull-down. Have I confused you?
Yes.
Yes? Who said yes? Someone say yes? Sorry, Brian. Do you know it's not that complicated? It's not that complicated.
No, it's actually easy.
So back to what I said. If we unplug that, and we see we've got 5 volts and 12 volts or whatever, or 2 lots of powers, what is it? It's a pull-up circuit. Because it's, sorry, pull-down circuit, because the switch is pulling it down to ground. The Hall effect sensor is pulling it down to ground. So pull down. If we open the circuit and they only have power and no other, none of the other wires, which are normally 3 wires, none of the other wires have any power, it's going to be the opposite. Be a pull-up sensor. All right. I'm going to move on now. I'm going to hope that that's just the basic foundation. I hope you can understand. I threw that Hall effect sensor in there just to add another dimension to what I'm saying. Everything in an electric circuit has the same fundamental basics about the circuit, okay, that we need to understand. All right? Be kind, you two. All right. Brian asked me about relays before. They're not that complicated. Most relays have a bit of a diagram on them. I don't know if they all do. Where's that relay I had before? Oh yeah, see on the end there, there's a bit of a diagram. You see that?
Yes.
But that, even if they don't, they're all the same.
Thumb finger, where are you?
We have number 30. We have number 87. We have 85. We have 86. They're a universal number on a relay, okay? Some relays will have another terminal, okay? They'll have 87A.
5-pin relay.
Okay, they'll have 5 pin. I'll explain that soon, but I won't confuse you with the extra pin at the moment. But each of these relays, see the numbers? 30, 87, 86, 85. So we have to have a ground. we have to have power going in to actually, there's an electric solenoid, okay? So we have, what happens if I have a coil of wire like that, and I put power there and ground there, what will that do?
Current will flow.
Sorry?
Current will flow.
Current will flow, and what will happen to that coil of wire?
Energize.
Energize. What do you mean by
It
energize?
will load.
What do you mean by load?
It will
Up current.
What happens when I put currents through a coil of wire? What happens to ignition coil when I put currents through that coil of wire?
Produce,
Energized.
What do you mean by energize?
magnetic field.
Magnetic field. It creates its own magnetic field, okay? Meaning that all around the outside of that is a magnetic north and south pole magnet. It's a magnet, okay? Because it's a magnet, I will have, for example, I will have two contacts and they'll join together, okay? One contact will be terminal 30 and one will be 87. Here we'll have 86 and maybe 85. See that? See that? There's that terminal. So when the magnetic field is turned on, that magnet draws the contacts together. When the magnetic field collapses, they open. And that's how a relay works. It's just a switch. Quite simple, okay? They can play up, they go wrong, but that's what the relay does. And that's a typical layout of a relay. But also we have, remember I told you about 87? We have a 5-wire. A
Yeah.
5-wire relay just gives us a second switch.
Yes.
Just a second switch. And if we put 2 bulbs on each circuit, we can switch between the two.
One will go off and one will turn
Yeah,
on.
exactly. So when we turn the relay off, it flicks back to that switch.
Yes.
And vice versa. That's all that is. Does that make sense? Alright.
Signal.
I know relays very well. I can't believe I got that so wrong.
Signal ಬರ್ತಿದೆ.
Okay.
Release.
So, automatic relays. What about flasher unit? It's a type of relay, isn't it? It's a type of
Yeah.
switch. How do they work?
On and off.
They go on and off, that's right. Okay, and they can be mechanical, like a relay. They can be electronic, and they can be thermal. A relay has to be able to regulate the flashing at a certain speed. And the flashing units are designed to control the flashing rate of a vehicle, directional indicators. This is achieved by providing a regular interruption in the electrical circuit of the indicator. So there's a bit of a diagram of a wiring diagram of a flasher unit. And okay, the flashes are required by law to flash between 60 to 120 times per second, each minute, sorry, I didn't mean seconds, each minute. So it's a certain rate it flashes, okay? But what happens if a bulb's blown? What happens if a wrong bulb's fitted?
Flash fast.
It will go a lot faster than that, okay? Probably up to about 150 times a minute or more. So if we see a flasher, one side flashing evenly, the other side much faster, 90% of the time is what?
Bulb.
A bulb. It's probably what you all need to know. It's a bulb, okay? Or a wrong bulb fitted, okay? We have computers now. You're interested in what we're looking at? He doesn't look at girls here.
Boys, not your boy.
All right. So, does that,
Hi.
all right. Have I got any questions? Okay. Whenever we do any work, what do we do when we finish? We have to check that our work has been fixed. Whatever the fault was, we have to make sure we've rectified that fault. We have to carry out a visual examination of where we fixed up and everything else, and that we've not left our tools behind, left dirty marks in the car, all those things. And we also have to confirm that there's no other problems. Sometimes we can introduce problems by what we do. We fix up a wire, we bumped another terminal off, or we haven't forgotten to put something back together again, or a plug not in properly. Make sure everything's working properly, that we have no new problems. So to do that, we need to road test the car, we need to check the air conditioning, we need to check the flashes, the lights, whatever. We need to check everything is working okay, the car's driving okay. Make sense?
Yes.
Who does that? Or who doesn't do that? Okay.
I don't do it.
Guess what?
Are we all good?
Guess what?
We are not good.
Are we all
Very
good?
good.
We all good?
Pretty good.
Have I lost everyone?
Lost and found.
We lost and we found it.
Okay. Oh, question time.
Why did the
Okay.
aircraft finish?
Why did the electric car finish the race early? Who knows the answer?
Battery flat.
Finish the race early.
Electric
Because they are very light.
How about I reword that? How come the electric car won the race early?
Because they are very light.
Sorry?
three-phase motor.
We'll have a look, eh?
You went early.
There's the electric car ready to take off,
Charge.
and he found a short circuit.
Nice joke.
There is no finish of the race.
Congratulations. Any questions?
You get
Mother
me.
chot.
Any questions? All good?
All good. Yes, sir.
Nice.
It's a better joke than
All right. We'll turn the camera off.